Right. Specific heat capacity and latent heat capacity, the best way of actually starting them out is actually looking at this graph over here. So this here is a temperature slash energy graph with time. So if you have water and it's frozen and you heat it up, it gets to this point and then it does this, and then you heat it up, you're providing a continuous heat all the way across. However, the graph does something like this. So we're going to explore why we have these flat areas over here and over here. So this is our first flat area, this is our second flat area, and we have these constant increase in temperature areas as well. So this here is where all of the energy is actually heating the particles up, so the temperature of the particles is increasing. However, when we get to this point and this point, there's actually no increase in temperature, and that's because the bonds in the particles are actually breaking. It happens going from a solid to liquid, and it also happens in area number 2 where it goes from a liquid to gas. So all the energy is going to breaking the bonds. That's why there's no increase in temperature. So what happens from this point to this point, this point to this point, and this point to this point? Well, in these points, the temperature is increasing. So we've got delta T, and it's the equation we're going to use here is Q is equal to MC delta T, which is a specific heat capacity equation. Where we have no temperature change, we use the latent heat formula, and it's just a very simple Q is equal to ML or MLV or MLF. So LF is the latent heat of fusion, and LV is the latent heat of vaporization. So I'm going to talk to you more about that in a bit, on which one you should use and why.